Hi, and welcome to Breaking VSM by attacking SecureKernel. We are Saar, Amar, and Daniel King, security researchers from the MSRC, and we are very excited to share with you today our story about hardening SecureKernel through offensive research. We have so much to cover today. We are going to see the shortest introduction ever to the architecture of VSM and the SecureKernel. Then we are going to talk about two of the vulnerabilities that we found, both by fuzzing and by statically auditing the code. And we're going to have some fun and again arbitrary code execution in the SecureKernel by exploiting both of those vulnerabilities. And then, of course, some takeaways. What you can take from this talk in order to kick off your own SecureKernel research at home, and what we can take from this talk as Microsoft in order to improve the security in our products. So, without any further ado, let's talk about VBS. So, in the new architecture of Windows 10 and VBS, we use virtualization in order to enforce isolation and restrictions in the operating system. VSM introduces VTLs, which are virtual trust levels, which we use in order to isolate the operating system into different isolated security contexts. As for today, we have two VTLs. We have VTL 0 for the normal world and VTL 1 for the secure world. In the normal world kernel space, we have kernel, just as you know it, and we can call it now the normal kernel. And in the normal world user space, you have your own user space. You have your programs, IDA, etc. In the secure world, we keep all of the most privileged and trusted components, which we really want to protect and isolate from the normal world. So we actually assume here that attackers already gained read-write primitives in the normal world kernel space, and we want to restrict them as much as possible. And all of that is being managed by Hyper-V. So you have kernel runs in ring 0 VTL 0. You have the secure kernel runs in ring 0 VTL 1, and Hyper-V exposes two hypercalls for normal calls and secure calls, which are services provided by each kernel to the other. The normal kernel clearly needs many services from the secure kernel for all of the most privileged functionalities it can no longer do. And the secure kernel still needs many services from the normal kernel because most of the functionalities are actually remained in the normal kernel because we really want to keep the secure kernel as small as possible in order to decrease its attack surface. Okay, now the hypervisor exposes hypercalls for the secure kernel to restrict VTL 0, and the secure kernel uses those hypercalls in order to restrict VTL 0 access to the both of the physical address space and to system registers. This is exactly what let us create great mitigations such as HVCI, which means that all of the pages that are marked as executable in a VTL 0 EPT have to be signed. It means that we can hide secrets in a secure world user space and mark all of those pages as unreadable to VTL 0. And clearly, compromise of either one of the secure kernel or of the hypervisor bypasses those mitigations and break the model guarantees. And this is the motivation for this research. Okay, so our story begins with a great teamwork. Daniel wrote an amazing fuzzer called Hyperseed. Its main purpose was to fuzz the hypercalls interface exposed by Hyper-V. I really encourage you to catch this talk by Sean and Daniel from OffensiveCon 2019. It was absolutely amazing. They found many issues in Hyper-V. And when I joined the team, I just saw this incredible work, and I pinged Daniel, and I asked him, hey, did you try to use Hyperseed to fuzz the secure services interface exposed by the secure kernel? Because this interface is actually very similar to the hypercalls interface exposed by Hyper-V. And 2 weeks later, Daniel here just got back to me with, hey, I just found 5 different bugs, VTL 0 to VTL 1. It was absolutely amazing. It proved to us that there is still much to cover in this area. So we teamed up, we found more bugs, and now we have a great story to tell. Now, bugs aren't really interesting if we can exploit them. So let's talk about exploitation. And before we start to do this classic circle of life, let's stop for a minute and ask ourselves what we can do, assuming that we gain read-write primitives in ring 0 VTL 1. And in order to answer this question, we really need to talk about mitigations. Because as you know, we have great mitigations in the normal kernel, but unfortunately, not all of those mitigations made their way into the secure kernel. For instance, the secure kernel image binary does go through randomization on every boot, but there are still many hard-coded addresses. We don't have CFI, and unfortunately, we don't have stat enforcement, which is one of the key features of VBS. So let's dig in here. All of those addresses are hard-coded in the secure kernel. There are even more addresses which aren't hard-coded, but they still can be predicted because of the so predictable and deterministic boot process of the secure kernel. I really want you to take a closer look into this shared page VTL 0 mapping. This is a very special page as it's a 1-to-1 mapping of the shared page from VTL 0 to this fixed virtual address in VTL1, and therefore every byte that you write to the shared page in VTL0 simply appear at this fixed virtual address space in a secure kernel. This introduces a great exploitation primitive of control content at a known address, which we usually need to invest some time before we can gain such a primitive. And there is the POC of that. In the first debugger, which is attached to MSRC, we just write arbitrary value. In the second debugger, which is attached to the secure kernel, we just read this value, and everything works great. Okay, let's talk about SLAT enforcement. In our model, we only have EPT enforcement on lower VTLs from higher ones. This is exactly how we implemented mitigations such as HVCI, Kardashian Garden, etc. But this means that the secure kernel, being the most higher VTL that we have today, isn't EPT enforced, which means that the PTEs in VTL1 have the final say. This actually tells us that given the arbitrary write primitive in a secure kernel, we just can create read, write, execute chunk of memory in the secure kernel, and we don't even need a read primitive for that because the PTE's base is fixed. Okay, this is super interesting, and just actually raises another question. What about RxOX? Because as we know, many researchers found several addresses that were marked as both writable and executable in the VTL0 PTEs. And this is actually fine because HVCI does a great job of mitigating this by SLAT enforcement. But if we could find this pattern, the same behavior in VTL1, then we really have something here. And indeed, we found 4 different addresses in VTL1 that were marked as both writable and executable in the PTEs. We fixed them all by now, of course, but this is just another great value of this research. Okay, let's talk about setup. Setup is super important. We chose to use hyperseed. It's super convenient. We can write all of the POCs and exploits in user space, and we have our own kernel space driver, which wraps all of the secure calls for us. If you don't want to go through all of these troubles, you can simply debug MSRC, breakpoint on key functions, and patch the registers in memory in runtime to trigger certain flaws in the secure kernel. We don't ship the secure kernel release binaries with the debug stub compiled in, but you can still achieve that, and your own machine is at home by using nested virtualization, KVM, QEMU. Many researchers are doing that. Here are some links that you can follow. And now with this new spirit, let's go over to Daniel, which will tell us about the first vulnerability and the first exploit.
Thanks, Saar, for the introduction. I am Daniel. Now let me walk you through the first vulnerability and exploit. In this talk, we will discuss 2 vulnerabilities. They are very different from each other. The only common part is that they are in the same function. The vulnerable function is named skmm obtain hot patch undo table. It is a long name, but you can tell it is related to the hot patch implementation. The function obtains an undo table. This table describes addresses that will be affected by reverting a hot patch. The first vulnerability is an auto-bound write. It is found by fuzzing with hyperseed. The second vulnerability is related to MDL unmapping. It is found by source code review. Generally, secure calls use transfer MDL to transfer data from VTL0, the NTOS world, to VTL1, the secure world. Those transfer MDLs are fully controlled from VTL0. Here in this vulnerable function in VTL1, it will first map the transfer MDL to VTL1 address space. It then constructs a new MDL and initialize it with the content stored in transfer MDL. At last, it will unmap and clean up this MDL. The security guideline here is to sanitize every field it read from VTL0, including the byte count field in transfer MDL. This is where the first vulnerability. This code snippet shows the first vulnerability. The byte count field passed from the VTL0 can be any value, and it will be used as the allocation length for the newly allocated undo MDL. Undo MDL should be at least 48 bytes as an instance of MDL data structure. Guess what will happen if byte count is smaller than 48? Yeah, you're right. Auto-bound write will happen. Let's see the MDL data structure layout. It represents information for our buffer in physical memory. It consists of 2 parts, the fixed header and the variable pfn array. The fixed header occupies the first 48 bytes and contains several important fields. Next is a pointer to another MDL. In this way, several MDLs can be chained together into a singly linked list, an S list. Size is the total length of the whole data structure. Mapped system VA points to the buffer after getting mapped into the address space. Byte count is the length of the buffer. Transfer MDL describes a piece of buffer transferred from VTL 0 to VTL 1. Here, the transfer buffer happened to be another MDL instance. The vulnerable function gets the byte count as the transfer buffer length and allocate a new undo MDL with the same length. If we specify the byte count to be 16, then a 16 bytes secure kernel pool will be allocated for the undo MDL. Here, I only discussed the situation that undo MDL is allocated in VS heap. I will explain the reason later. We can see that the next pool allocation is also shown here in blue color, with 16 bytes VS chunk header. The transfer MDL gets mapped into the VTL1 address space. Then mapped system VA can be used to access the transfer buffer directly. We call this transfer buffer the original MDL. Original MDL is also fully controlled from VTL 0. The undo MDL will be initialized according to the original MDL. Now we see how the auto-bound write happen when calling initialize MDL. The next pool allocation will be overwritten with the original MDL. The overwriting capability is 16 bytes. We see that the VS chunk header is still intact after the overwrite, which is very good for exploitation since this overwrite won't be detected by pool system. If we try the POC for the first vulnerability, we will see the typical bug check caused by access violation, and we will see the GSOD for Windows Insider build. The fix for the first vulnerability is also straightforward. Stop further processing if byte count is smaller than 48. The fix is more intuitive by comparing Adapro CFGs. What can we do with this arbitrary write to the VTL1 world? Saar has some considerable insight. This is all what a hacker need. Let me show you why. Now I have the capability to overwrite the neighbor pool allocation. What should I do first? Yes, I should select a good neighbor to be the overwritten victim. Since I am already familiar with MDL data structure, why not choose another MDL as the neighbor? We can overwrite the first 16 bytes of the victim MDL, including the next pointer, size, and flags. The initial primitive is ready and seems promising. Let me show you more essential backgrounds for the final exploit. Let me introduce the SKPG context a little bit. It is a core data structure used for SecureKernel HyperGuard. We already know that its address is predictable, a very good, stable target. I should take advantage of this fact. There are quite some interesting fields in it, including 2 callback routine function pointers. I have to be very cautious since it is self-protected. There is an embedded timer in it. The timer routine will be invoked when due time comes. The timer routine will trigger the runtime check routine. The latter will verify the data integrity of the whole data structure. It will fast fail if anything wrong. Corrupting any fields of the SKPG context will be noticed by the runtime check routine, except those 2 callback pointers. In fact, if I replace one of those 2 function pointers, the whole self-protection is bypassed. Those 2 callback pointers are good candidates for redirecting control flow to shellcode. I have mentioned SecureKernel pool. Now let's take a closer look. SecureKernel uses segment heap, which is typically comprised of variable size heap and low fragmentation heap. In VS heap, allocations of different sizes are put together side by side. In RFH heap, allocations of the same size are put together, and allocations of different sizes are separated from each other. In SecureKernel, the tag and pool type arguments are ignored. Pools are always allocated in paged pool. Since undo MDL is 16 bytes, while I cannot make the victim MDL smaller than 48 bytes. If I want to put them together, I have to use the VS heap. During the exploitation, the main challenge here is in secure world, there is too few allocations. I create two WinDebug JavaScript extensions to help dump out the LFH and VS heap layout. You don't need to understand the meaning of every field here. I just want to show you how scarce the pool allocations are in secure world by default. In the upper screenshot, only 15 out of 129 LFH buckets are activated. They are highlighted in red. In the lower screenshot, only 22 segments used in the VS heap. Each segment ranges from 16 to 64 pages. The fewer the pool allocations, the lesser possibility for push shipping. For good push shipping, I have to find out a persistent and controllable pool allocation. Create secure image secure call can be used for this purpose. It can allocate arbitrary sized pool allocations. The minimal allocation size is 48 bytes. A handle to each create secure image is returned to the VTL0. Closing this handle will free the corresponding secure image allocation. I can use this allocation to make holes of 16 bytes. Another secure call, left-dump start, will allocate a list of MDLs with controllable MDL size. Those MDLs are good candidates for being victim MDL. There are two challenges here during push shipping. First, there is a guard page after each VS heap segment. If the undo MDL is allocated at the end of the segment, it will corrupt the guard page and cause backcheck. Second, I cannot make too much allocations of the same size. Otherwise, it will activate LFH bucket if over threshold. This is how I do the push shipping. I have pasted some Python scripts here for reference. First, I make two series of pull allocations with create secure image secure calls of different sizes A and B repeatedly. Then I replace all of the B allocations with the left-dump MDL of the same size. Then I replace all of the A allocations with smaller D allocations, making 32 bytes holes, which is suitable for undo MDL, including the VS chunk header. Further undo MDL allocation will be allocated in these holes and corrupt the neighbor left-dump MDL with the first vulnerability. ASCII left-dump start. This secure call will allocate a list of MDLs and chain them into the singly linked list. ASCII left-dump add buffer. This secure call will try to allocate a target MDL from the S list and write to the PFN array at the end of that MDL. Left-dump context is a global symbol. It contains a pointer to the S list. Pages added in the left-dump context determines where to write to when calling left-dump add buffer. Byte count in each MDL determines its capacity. After filling up its capacity, the writing cursor will be moved to the next MDL in S list. The calculation of writing cursor is demonstrated here with this pseudocode. With the push shipping approach I discussed, it is possible to make the left-dump MDL the victim MDL and allocate it after the undo MDL. Trigger the auto-bound write will modify the next pointer of the victim MDL. S list will be diverted to a pivot MDL under our control. If we make the pivot MDL in the shared memory, which is writable from VTL0, we can fully control its content, including the next pointer and byte count. This modification will be reflected to the VTL1 in real time, which can be used for repetitive adjustment of the next pointer and overwrite to arbitrary address. But the shared page is read-only from VTL1. Writing to the PFN array of the pivot MDL will backtrack due to the access violation. There is a trick here. We can modify the byte count to be smaller than page size. which makes the power to MDL's capacity 0, and it will be skipped directly to the next MDL. Now we have full control of the power to MDL, and we can retarget worker MDL by modifying next pointer. We can write to anywhere, but we need to know when to modify the next pointer. We use the second shared memory as the worker MDL and detect if its PFN array has been overwritten after we call the left dump at buffer. Once we detected that the worker MDL has been overwritten, we add power to MDL byte count with page size. It makes sure next time we call left dump at buffer, we are still writing to the beginning of the worker MDL's PFN array. In theory, we can write to anywhere. The only constraint here is the worker MDL byte count should not be smaller than page size. Otherwise, it will be skipped, and writing will be redirected to its next MDL. Normally, this constraint can be bypassed if we can find some non-zero content before the overwriting target, crafting a worker MDL there and adjusting the writing cursor by changing the byte count accordingly. You can see I take fully advantage of the shared pages. I use the first shared memory to craft power to MDL and modify worker MDL repeatedly. I use the second shared memory as the tentative overwriting target and determine the good timing to modify the next pointer when the worker MDL has been activated. After the worker MDL has been activated, I can do repeatable write what where. Where is determined by the next pointer and byte count of the power to MDL. Writing cursor is pointing to the overwriting target. What is parsed as parameters to the left dump at buffer secure core. Here, I use just one page frame number, which is exactly 1 keyword. This is the overwriting content. Trigger the left dump at buffer secure core, which will do the final overwrite. In this way, I can do the write what where trick accurately and repeatedly. A little summary here. First, I corrupt the next pointer of the MDL, get one arbitrary write. Then I fake a power to MDL in the shared page, where I can modify repeatedly from VTL 0 by design. With this arbitrary write, I corrupt a node in the left dump context MDL chain and make it point to the power to MDL in shared page. Call left dump at buffer to trigger the arbitrary write, changing the shared page content to adjust the overwriting target. Call left dump at buffer again to trigger another overwrite. With this arbitrary write capability, I modify page table entry of the shared page to executable, place a piece of shellcode there. Then I modify the skpg context callback routine and jump to the shellcode. In this way, arbitrary code execution is achieved. This is the demo shellcode. It first modifies the skpg context callback routine. Then it leaks the SecureKernel base pointer back to VTL 0 through shared page. It resets timer, configure 5 seconds relative due time. Shellcode will be invoked every 5 seconds. And shellcode is fully controlled from VTL 0 and can be refactored for any purpose. The first vulnerability was fixed in January 2019. The SecureKernel pool then switched to segment heap in the middle of 2019, and the exploit push-shipping depends on the segment heap. This demo is against build in May 2020, where the first vulnerability has already been fixed. A trick to undo the fix is by WinDebugger command. This command will erase the fixed code to not slide. So this exploit approach works well on latest build, but the vulnerability is already gone. No customer will be at risk with this demo, since no build is both vulnerable and exploitable. Here is the demo. I have pasted screenshots of important output here as background. I will play the demo video. This video has been edited to look smoothly. SecureKernel debugger is attached here, and the fix has been unpatched by the debugger command. Before the exploit, the shared page is filled with zeros rather than the shellcode, and the shared page is not executable. I will play the demo video now. I run the first Python script, which will do the push shaping, place left dump MDL after the hole, and trigger the first vulnerability and modify the MDL next pointer. It takes some time for the push shaping. Then I run the second Python script, which will detect if the tentative shared memory has been modified or not. If it has been modified, I can do further arbitrary write what where. The third Python script will modify the shared page PTE to executable. And the last Python script will redirect the skpg context callback routine to the shellcode I prepared in the shared page. After the due time comes, the shellcode gets executed successfully. Now the shared page is executable, and it is filled with the demo shellcode. And this piece of shellcode is invoked by redirecting the skpg context callback routine. And this shellcode will get executed periodically. I can modify the shellcode from VTL0 freely at any time for any purpose. In this way, arbitrary code execution is achieved. Okay, this is my part. I will transfer control to Saar. Thank you.
Thank you so much, Daniel, for this great analysis and exploit. So yeah, we fixed this issue, and now we make sure that the transfer MDL byte count is valid. But there is something else which is super interesting in the general flow in this function over here. And this is something which is related to the way that we map and unmap VTL1 MDLs. Let's take a closer look. So this is the general flow in SKMM obtain hot patch undo table. And as you can see, we just allocate some chunk in a secure kernel heap. We copy the entire transfer MDL into this new chunk. We make some integrity check, and if this check passes, we call SKMM map MDL to map this new MDL into the VTL1 address space. And if this check fails, then we do go to cleanup, we take the bailout flow, and we hit the call to SKMM unmap MDL. Now, the problem here is that we don't make sure that we indeed called SKMM map MDL before calling SKMM unmap MDL. And this is exactly what is going to happen if the integrity check fails. Now, since we can control over the entire undo MDL over here, we can make this integrity check fails, and therefore it just summed up to be the ability to call SKMM unmap MDL on a fully controlled MDL by VTL0. Okay, great. And here you can see the code. At the beginning, you can see the integrity check. At the end, you can see the call to SKMM unmap MDL. And right there in the middle, there is the call to SKMM map MDL, which we clearly skipped. Okay, POCs. We have to write POCs for everything that we find, because otherwise everything is meaningless. So let's cuff the MDL, set up for one in the virtual address in the map system VA, trigger the vulnerability, and boom, we got the exact expected call stack in the crash from the vulnerable function to SKMM unmap MDL, and then page fault in node page area on the virtual address AO, which is the PTE address of the virtual address 4141 from the MDL. This happened because SKMM unmap MDL resolves the PTE address of the virtual address in order to write 0 into the PTE. Okay, great. Knowing this, we can create another POC. Let's try to crash some arbitrary flow in the secure kernel. And for this to happen, we really need to find some virtual address which is being used by something in VTL1. I just chose here the shared page. VTL1 has its own shared page. It's this fixed virtual address. Set it up in the MDL, trigger the vulnerability, and again, we got a crash in some arbitrary flow in the secure kernel, in some thread that tried to dereference the shared page. And of course, this page is no longer present because we wrote 0 on its PTE. Okay, great. So we have the vulnerability, we have the POC, we know everything, and now it's the time to get the actual work starting. So please note that we don't have here a memory corruption with a control content primitive yet, but we can clearly build one. And in order to build one, we really need to understand the functionality of SKMM unmap MDL. Now this happened to be super simple. This function simply scans all of the PTEs discarded by this MDL. It writes zeros over all of those PTEs. Please note that after this step, every dereference to every single page discarded by this MDL will panic because all of the present bits in all of the PTEs are zeros. And then we can choose if we want to take the call to SKMI release unknown PTEs, which in addition to the zeroing out of all of the PTEs, goes to the bitmap and clear all of the relevant bits just to indicate to the PT allocator, hey, all of those PTEs are ready to be reclaimed and reused. Okay, great. Please note that all of the writes done by SKMM and MDL are safe in the sense that all of the writes to all of the PTEs will for sure fall inside the PTE's range due to the nature of the calculation, which converts from the virtual address to the PTE address. And all of the writes to all of the pages ref counts will for sure fall inside the PIF and DB range due to an explicit check in the code. But we don't really need that. We can zero out arbitrary PTEs, and therefore we can clearly create some use after free scenario by replacing the underlying physical page. And if we want this to happen, it would be very good of us to take the call to SKMA release unknown PTEs just to make sure that the PTE allocator can reuse those PTEs. Okay, now it's the time to talk about some structures. The secure kernel maintains some structure in order to manage its own virtual address space. Makes sense. One of those structures is the PTE range. This structure simply describes a range of PTEs of a certain use. There are some examples right over here. And this structure has exactly what you expect from it to have. It has a pointer to all of the PTEs. It has a pointer to the bitmap, which indicates which one of those PTEs are free and which one is in use. And this is really important for us here because the function skmi release unknown PTEs try to resolve the PTE range, which contains the PTE address of the virtual address from the MDL. And here you can see that this function only looks for specific 3 PTE ranges, which absolutely don't cover the entire virtual address space. There are more PTE ranges. And even after this function chooses one, it doesn't really make sure that the PTE address is inside the PTE range. It's only check against the base. So I can just choose a virtual address, which its PTE address is outside of all of those 3 PTE ranges, set it up in the MDL, and therefore I gain the ability to write relatively to the bitmap of one of those PTE ranges. So we gained a relative write primitive. Fantastic. And there is the POC. From the vulnerable function to SKMM unmap MDL, and then page fault in node page area during the clearing of the bitmap. Okay, fantastic. This is super great, and it's really cool and really awesome, but it actually doesn't help us a lot because there are so many pages outside of all of those bitmaps of those specific 3 PTE ranges that aren't mapped and they are not in use at all. So I really could make it work, of course, but I really prefer to do better tricks, and therefore I just do the use after free idea. It would be much, much better. And I'm going to target the SKMI system PTEs since it's the main PTE range in the secure kernel. So we know exactly what we have to do, right? We need to find some interesting structure. We need to trigger the vulnerability and unmap the underlying physical page, reclaim the PTE, use after free, profit. Fantastic. And it would be a very smart idea of us to understand the allocator involved here because we need to reclaim the PTE. So let's talk about the PTE allocator. This happens to be very, very simple. There are 2 functions, the allocation function and the free function. And the allocation function simply checks out the bitmap hint value from the relevant PTE range. And it uses this value as the first index to scan from in the PTE's bitmap and just looks for sequence of enough zeros. Note that this bitmap hint value wraps around only when the allocation function reaches to the end of the PTE range. And you can see this in those debug traces. You can see that all of the allocations are continuous, independent of all of the frees in the middle. Okay, great. Now, we really want to get a good crash. Page fault in node-page area really isn't good enough, and it really doesn't interesting. So I have here 2 options. I chose not to allocate the target structure myself, because if I will also need to spray a lot in order to make the bitmap hint to wrap around. And I really prefer to do better tricks and stable exploits. So I simply can rely on the fact that the secure kernel boot process is so predictable and so deterministic that actually every time after boot, I have about the same bitmap hint. So I can just look over the entire address space that I have after the bitmap hint that I have after boot and just see if I have already existing structure that it's in used and that it comes after the bitmap hints. And of course, I found the PRCB structure, which is a great candidate for memory corruption exploits. Please note that I can't corrupt specific data. I have to corrupt at least 1 page due to the nature of the vulnerability. But it's actually fine because this structure is very, very large. It spans over a few pages. And I can, of course, choose the specific page which is best for me to corrupt. Okay, great. So we know what the high-level plan here is, right? Okay, let's see it in action. So this is a bitmap of all of the PTEs in SKMI system PTEs PTE range. There is the bitmap hints that I have after boot right there. So let's spray just to get closer to the PRCB pages, trigger the vulnerability on the expected virtual address, and keep spraying in order to reclaim the PTE of this single page inside the PRCB pages. And by implementing this in code and run the POC, we got finally a great crash of dereferencing arbitrary pointers. From this point, it's very trivial to gain read-write primitives. And from this point, we know exactly what we need to do. We don't have time to see the full exploit, but we already saw what we can do with read-write primitives, so it's game over. Okay, now let's talk about what you can do after we gain arbitrary code execution. So of course, we can bypass both HVCI and conditional guard, as we said, because the secure kernel by design have the ability to issue hypercalls for the hypervisor and setting arbitrary permissions in the slots. Of course, fantastic. We keep work on hardening the secure kernel. We fix all of the issues we found in this research. We truly believe that there is so much high values in developing end-to-end exploits, and one of those is to spot an important behaviors to change. So we made these 4 both writable and executable addresses to be non-writable. We are investigating right now options for randomization of secure kernel regions. There are actually more surprises to come, so please stay with us. And of course, if you have bugs, please submit to us. We really want to work together. And just like we said, DOS isn't in scope because VTL0 can, of course, by design, DOS VTL1. So we need to find POCs which actually can leak sensitive data or can corrupt memory, and etc. Okay, great. This research could not have been done without a great folks. So thank you all so much. And now would be the time for Q&A. Thank you so much.
Thank you. Hi. Thank you so much for attending the talk. We don't see any questions that we didn't answer, right? If there is some clarification that you want to make, some question, some issue, please write it right now in the chat. It might be worth to mention that we are about to upload the slides in about 5 minutes or so you can find it on Twitter. Are there any questions? Okay, so you could find the slides again on Twitter. It will be on the MSRC GitHub. And thank you so much. Thank you. Oh, wait, I see. Are there plans to extend the VTL0 mitigations to VTL1 secure kernel? Yes, so this is a very good point. Yes, as I said, at the end, we are working on porting some of the normal kernel mitigations into the secure kernel. We are starting with investigating some randomization for all of the fixed addresses and all of the predictable ones. And there are some more surprises to come. The devs team are working on that. Stay tuned for some interesting news in the near future. Yes, so just like I said, KSLR will for sure. They are working on it right now. CFI, it's an interesting point. Yeah, we definitely want to have CFI there. The like interesting point is that unlike the K CFG that we will have in the like a normal kernel, and we can protect like over the bitmap with the extended page tables, we can't do that for the secure kernel because there isn't slat enforcement. But we can sure have like a normal CFG there. It might happen in the future as well. Okay. Okay, great. So thank you so much again, and enjoy the rest of Black Hat. Bye bye.